Picture a factory where every station adds a tiny, almost trivial piece to a product, and somehow by the end, a beautiful, complex item appears. What if I told you that the same trick is what powers neural networks? Many simple steps stacked together that learn to build something smart. Imagine a small sandwich shop owned by Maya. On a busy morning, she's juggling orders: avocado toast, turkey sandwiches, vegan wraps. She has a row of stations along a counter. One person slices bread, another smashes avocado, one spreads mayo, another layers lettuce and tomatoes, and at the end, someone wraps the sandwich and hands it to the customer. Each worker does a simple, repeatable task. Alone, none of these tasks make a sandwich, but in sequence they create the finished product. That's our setup, a friendly, relatable scene where simple steps become a finished item. Now we'll use that scene to explain neural networks. In our factory, think of each station on the line as one layer of a neural network. The earliest stations do tiny, straightforward jobs. They see raw ingredients and do something small and predictable. Later stations combine those small results into bigger chunks, and the final station produces the finished sandwich that either delights the customer or misses the mark. Neural networks do the exact same thing with information. Early layers detect super simple patterns. Middle layers combine those into parts, and late layers assemble those parts into a final decision, like this picture is a cat or this email is spam. Let's map the roles directly. Each worker at a station is like a neuron, a tiny unit that looks at its inputs and decides what to pass along. Ingredients coming down the line are like input data, raw pixels of an image, words in a message, or numbers in a spreadsheet. The instructions each worker follows, how firmly to press the avocado, how thin to slice the bread, are like weights. They control how much influence each incoming item has on what the worker passes forward. If a worker spreads too much mayo, the sandwich changes. If a weight is too strong, a neuron overemphasizes one input. When a worker receives a handful of ingredients, they don't always pass everything forward. They might decide whether that combination is worth forwarding. That decision is like an activation function. In plain terms, activation is the rule a neuron uses to decide if its output should be quiet, loud, or somewhere in between. Some rules are like thresholds. If there's at least this much avocado, pass it on. Others are smoother. The more tomato, the more flavor I pass forward. Different rules shape how the line behaves. Early station workers are specialists. One notices crust texture, another checks for bruised lettuce. In neural terms, early layers learn very simple patterns, edges, color contrasts, or basic word sounds in speech. Middle stations combine these basic checks into bigger features. Is there a slice of turkey with the right size? Does the assembled filling look like a wrap or a sandwich? For image tasks, this is where shapes and parts form. For language, where syllables assemble into words. Finally, the last station makes the judgment. Wrap it, label it, or send it back for rework. But how does the assembly line learn to make the right sandwich? Maya helps her team by tasting and giving feedback. Too salty. Needs more avocado. Nice and crisp. In a neural network, the equivalent is training. We show the network lots of examples. Pictures labeled cat and not cat, or correct and incorrect sandwiches, and then measure how wrong the final product was. That measure of wrongness is called loss. Loss is just a score that says, this output missed the mark by this much. Maya's feedback travels backward. If the sandwich is too salty, she tells the station that added the salt to use less. If it's soggy, she tells the worker who applies mayo to pass less on. Neural networks use a similar backward feedback system called backpropagation. Instead of workers, we adjust weights. Backpropagation figures out which weights contributed most to the mistake and nudges them in the right direction. The method it uses to make those nudges is conceptually simple. Try to slightly change each weight in the direction that reduces the mistake. This step-by-step nudging is called gradient descent. Picture a chef adjusting spice a tiny bit at a time until the flavor is right. To keep it all friendly, let's put the technical words into plain English. A neuron is a worker that takes inputs and makes a simple output. Weights are how much each input matters to that worker. Activation is the rule that decides whether or how strongly that worker passes its result forward. A layer is a group of workers sitting at the same station. The network as a whole is the entire assembly line. Training is the practice sessions where you give examples and correct the line until it produces reliably good results. Loss is the score saying how far off the product is. Backpropagation is the process of telling earlier workers how to adjust. And gradient descent is the gentle nudging of those adjustments. Here are 2 everyday examples to make it concrete. First, your phone's photo app that suggests tags for faces. Early layers look for bright spots and edges. Those are like the bread slicer and mayo spreader checking raw ingredients. Middle layers assemble those into eyes, noses, mouths. Like a station recognizing that the bread, lettuce, and cheese together look like a sandwich filling. The final layer says, "This looks like Jamie," based on how those facial features combine. The more photos the app sees, and the more labeled examples it gets, you tagging your friends, the better it nudges its weights and the fewer mistakes it makes. Second, a spam filter on your email. The first layers detect tiny signals, odd words, strange links, or suspicious spacing, just like workers sniffing out overly salty or soggy bread. Middle layers detect combinations like free plus click or bank plus urgent, which signal higher risk. The final layer takes all those clues and decides whether the message goes to inbox or spam. If a spam message sneaks through, that's like a customer complaining. Human reviewers or user flags act as feedback, and the filter adjusts its internal rules to avoid that error next time. You might wonder, why stack so many simple workers instead of making one superstar worker? 2 reasons. First, simplicity scales. A lot of tiny focused checks are easier to learn from examples than one giant complicated rule. Second, reuse. Early workers learn features that are useful for many tasks. The station that recognizes crispy edge helps whether you're making a BLT or a crunchy veggie wrap. In AI, early layers that learn edges and textures help across image tasks. They're reusable building blocks. There are a few more practical bits to gently mention. Sometimes the line needs regular restarts or adjustments. That's like resetting learning rates or reinitializing weights when training gets stuck. Sometimes a station becomes overconfident and ruins the product by always adding too much of one thing. That's overfitting, where a network learns quirks of the training set that don't generalize. To fix that, the shop might rotate tasks, test on new customers, or add variety, analogous to techniques like dropout and validation data that help a network generalize better. Let's loop back to Maya's shop. After weeks of carefully tasting, feeding back instructions, and nudging behaviors, the team becomes smooth. The first stations don't just slice bread, they slice it in a way that later stations recognize and love. The middle stations assemble fillings that the closer to end stations can wrap without fuss. Customers come back because the sandwiches are consistently good. The worker-based assembly line has learned, not because any single person memorized every sandwich, but because each station learned to do its small job better and better in the context of the whole line. That's the essence of a neural network. Many small, simple parts working in order, learning through examples and feedback, combining to make a reliable, intelligent result. Whether the task is recognizing a face, translating a language, or sorting spam, thinking of it as workers on an assembly line helps keep the idea concrete and human. So, next time you hear neural network, picture Maya's sandwich counter. Rows of friendly workers, each doing small chores, each taking tiny pieces of the puzzle and passing along better, clearer bits until the final station hands you a product worth smiling about. The magic isn't in a single genius neuron. It's in the layers, the teamwork, and the feedback loop that refines every small decision. If you liked this, hit like, subscribe, and ring the bell. Join Model Drift for more friendly AI stories that make complex ideas feel simple and useful.